memory is an array of slots, so to speak, and you put information in each slot. Each slot has 8 bits, or you can think of bigger slots as having being like just 4 groups of 8 bits, so 32 bits. And in this case, if it's int, it's like 32 bits. Okay, but you have slots, and memory is an array itself. So to represent vectors, we just need part of that array. So we just need to know where to start and how many slots we have. So in order to carry these names that correspond to vectors, we just have the address of the first slot in memory that will represent the 4 slots dedicated to our vector. That's why int star. It's not multiplication. It's int star means addressed, the address of an int. And what this function does is this. Okay, so if you start at so this is just what happens when you print the result of the function at if you pass it 0, this is what you get. If you pass it 1, this is what you get. 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. up to 16. Okay. So this is the first slot in memory. This is the second, third, and fourth. And maybe you can see if you replace the 1s by 0s and the -1s by 1s, you see it would be 0, 0, 0, 0, and then 1, 0, 0, 0, 0, 1, 0, 0. If you've ever seen binary numbers, it's kind of flipped, it's kind of written backwards, but it's a very standard enumeration. So one of the things that this means is, so it's basically binary, written with the -1s and 1s. And the way that works is simply that in the memory of the computer, an integer is just a pattern of 0s and 1s, a small array of 0s and 1s. And if we just look at the first 4 0s and 1s, then the first, so say, 3 will be, first is 1, second is 1, third is 0, fourth is 0, because it's like 2 to the 0 plus 2 to the 1 plus 0 plus 0. And so basically, if you want to convert that into a vector, you just have to go through this array, and every time you see 0, you put 1 in the vector at the corresponding position, and whenever you see 1, you put -1. So this is a standard for loop that loops over I is equal to 0, 1, 2, 3. In the thesis, it goes from 1 to 4 because mathematicians like to start at 1, and computers like to start at 0. Starting at 0 is more convenient sometimes, but ending at 4 is more convenient sometimes. But usually starting at 0 is more convenient. Doesn't matter. So here I want to explain this line, because what this is saying is you just go through um, these 4 values for I, all the components of this pattern of zeros and ones, and you just recreate a pattern of -1 and 1. And this thing, it should be read as, if this, then that, else this. And so it's this whole thing is an expression which has it takes in 3 arguments. The first argument is a predicate or a logical expression which evaluates to either true or false depending on the value of I. And true corresponds to 1 and false corresponds to 0. And if you get 1 or true, this whole expression is equal to -1, and if you get 0 or false, this whole expression is equal to 1. And so what is this logical expression? Really what it's saying is look at the ith position in the bit pattern. If you see a 1, then the answer is true. And if you see a 0, the answer is false. So how does it accomplish that? So it's this thing is simply, you start with the bit pattern where everything is 0 except the first component, and then you shift this thing by I positions, and so that you get a pattern where everything is 0 except the ith component, which is 1. And then you do a bitwise AND, sorry. And so you have this bit pattern, and you can kind of think of the first bit pattern, which is the integer you're interested in, and then you have this other bit pattern, which is just zeros and a 1 at the ith position. And then when you AND them together, each component, okay, you do a logical conjunction. So if it's 2 zeros, you get 0. If it's 1 and 0, you get 0. And if it's 1, 1, you get 1. So in effect, everything except here will be 0, and this will be whatever is left, whatever was at that position in N. So if you get this a full 0 sequence, then by convention in C, everything that is not 0 is equal to 1, is true. It gets converted to true. And so if it's false, if it's completely 0, you get 0, and if it's 1 somewhere else in the bit pattern, which means it's not fully equal to 0, it gets replaced by 1. So, or it gets interpreted as 1, in the sense that it will take this branch instead of this branch. Okay. And this explains why this looks like binary written backwards, because it is binary written backwards with this substitution of 2 symbols. Okay. Then it's this one is pretty straightforward. Static simply means that it's a so-called global variable. So there's just one place in the program in memory which corresponds to this name, and everywhere in the program people can refer to it and modify it and read from it, and that's it. Right. Just making sure it doesn't crash like last time. And so here it's just all coordinate pairs. is a matrix, basically an array, a 2D array, and this is what it looks like in memory. So 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. Okay, and I could have just written it like that directly in the code. And basically it's, if you have a vector in 4 dimensions and you want to see all the pairs of coordinates where the first is less than the second, then this is what you get. These are all the possibilities. You have 6 because 4 choose 2 equals to 6, and whenever you see 6 in the program, it's usually because of that. I simply did not think of defining something. Because you can't use these numbers to start something, I think. So I didn't know how to deal with that. But so this init all coordinate pairs simply computes this and puts it in memory. I could have written it just by hand, but this shows the basic structure. This is how you traverse all pairs. You just, the first index goes from goes through the first n-1 things, and the second index every time goes from just after the first to the end. This is what, and then it's a 2D array. So this k is the depth in the array, so the row number, if you will. And then this other thing, 0 or 1, is simply whether this or this. And as you can see, I have to increment k independently, and you can think about why that is. Okay, and so now I have a couple of functions that have the word footprint in them, and basically the footprint is if you have a vector which is in the set of possible vectors, and then you look at all the pairs of coordinates and compute the product. For each pair of coordinates, you get a vector of plus and minus ones, which has 6 components. And this is the footprint. This is what I call the footprint. So pairwise footprint. Pairwise because it's like for each pair of coordinates you do the product. This is what we do here, and it's either plus or minus 1. Alright, but then I want to be able to look at all the set of possibilities and sort of have different footprints and combine them into the set of all possible products for each components. And so I have to define the semantics in a way that corresponds to the correct mathematical idea. And the basic mathematical idea is that first of all we do the combination. If you have 2 footprints, we do the combination pointwise, in the sense that for each pair of components we look at 2 footprints. So if this one is plus 1 and this one is minus 1, it means that we have the possibility of getting plus 1 for this product and minus 1 for the same product. So the total set of possibilities is the union of these 2 singleton sets. Okay, and that's the basic idea. So the semantics is simply that plus 1 means the singleton plus 1, minus 1 means the singleton minus 1, and 0 means the